Welcome to this lesson on linear second-order differential equations. Today, we'll specifically focus on the case where the auxiliary equation has complex roots. This is an important topic in differential equations with many applications in physics, engineering, and other sciences. Let's start with the general form of a homogeneous linear second-order differential equation with constant coefficients. It's written as y double prime plus p times y prime plus q times y equals 0, where p and q are real constants. To solve this equation, we need to form what's called the characteristic or auxiliary equation. We make an assumption that the solution has the form y equals e raised to the power rx. When we take derivatives, we get y prime equals r times e to the power rx, and y double prime equals r squared times e to the power rx. Now, we substitute these expressions back into our original differential equation. We get r squared times e to the power rx plus p times r times e to the power rx plus q times e to the power rx equals 0. We can factor out e to the power rx since it's never 0, and we're left with r squared plus p, r plus q equals 0. This is our characteristic or auxiliary equation. Now, let's focus on the case where this quadratic has complex roots. This happens when the discriminant delta is negative. The discriminant is given by p squared minus 4q. When delta is less than 0, the roots are complex conjugates, given by r equals alpha plus or minus I beta. The values of alpha and beta can be calculated directly from the coefficients of our original differential equation. Alpha equals negative p divided by 2, and beta equals the square root of 4q minus p squared, all divided by 2. When we have complex roots, we get a general solution that involves both real and imaginary parts. Two independent solutions are e raised to the power alpha plus I beta times x, and e raised to the power alpha minus I beta times x. However, since we typically want real-valued solutions, we take the real and imaginary parts to get our general solution. Y of x equals e raised to the power alpha x times the quantity c1 times cosine of beta x plus c2 times sine of beta x, where c1 and c2 are arbitrary real constants. Let's visualize what this solution looks like. The term e raised to the power alpha x represents exponential growth when alpha is positive and exponential decay when alpha is negative. The sine and cosine terms create oscillations. When combined, we get oscillations that either grow or decay exponentially depending on the sign of alpha. Let's work through an example to see how this method is applied. We'll solve the differential equation y double prime minus 2, y prime plus 5, y equals 0. Step 1, we form the characteristic equation. We get r squared minus 2, r plus 5 equals 0. Step 2, we compute the discriminant. Delta equals negative 2 squared minus 4 times 1 times 5, which is 4 minus 20, which equals negative 16. Since the discriminant is negative, we have complex roots. Now we can find the roots using the quadratic formula. R equals 2 plus or minus the square root of negative 16, all divided by 2. This simplifies to 1 plus or minus 2y. So alpha equals 1 and beta equals 2. Step 3, we write the general solution. Y of x equals e raised to the power alpha x times the quantity c1 times cosine of beta x plus c2 times sine of beta x. Substituting our values, we get y of x equals e to the power x times the quantity c1 times cosine of 2x plus c2 times sine of 2x. Let's visualize our solution with different values of the constants c1 and c2. The blue curve shows the solution when c1 equals 1 and c2 equals 0. The red curve shows the solution when c1 equals 0 and c2 equals 1. The green curve shows the solution when both c1 and c2 equal 1. We can verify that our solution is correct by substituting it back into the original differential equation. This involves differentiating twice and showing that the equation is satisfied. The process is algebraically intensive, but with careful application of the chain rule and trigonometric identities, we can confirm that our solution indeed satisfies the original differential equation. Let's summarize the steps for solving linear second-order differential equations with complex roots. First, write the differential equation in the standard form y double prime plus p, y prime plus q, y equals 0. Second, form the characteristic equation r squared plus p, r plus q equals 0. Third, If the discriminant is negative, compute alpha equals negative p over 2 and beta equals square root of 4q minus p squared over 2. Finally, write the general solution as y of x equals e to the power alpha x times the quantity c 1 times cosine of beta x plus c 2 times sine of beta x. This method has numerous applications in physics and engineering. For example, in the study of damped harmonic oscillators, such as a mass on a spring with friction, or in electrical circuits with resistors, inductors, and capacitors. In these physical systems, alpha determines whether the oscillations grow, decay, or maintain constant amplitude over time, and beta determines the frequency of the oscillations. In conclusion, we've learned how to solve linear second-order differential equations when the auxiliary equation has complex roots. This method gives us solutions that exhibit oscillatory behavior with exponential growth or decay, depending on the sign of alpha. Understanding these solutions is crucial for modeling many physical systems, from pendulums to electrical circuits. Thank you for watching, and I hope this has helped you understand this important topic in differential equations.